So welcome, dear friends. This is a very basic question I had raised, and this has to do with your understanding of what is a property. This has been asked because we are going to discuss uh, the derivation of the property called as entropy using the Clausius theorem. Okay, so this is the reason why I asked you this question, because without knowing what is a property, you won't appreciate what we are going to discuss today. So the plan is we would be discussing first how is property identified, and then taking up our discussion on Clausius theorem, we would be moving to the proof of, or we would be rather deriving the property called as entropy. So this is the plan of today's session. Okay. So after conclusion of this poll, I am not concluding yet. Okay. I would be starting with the discussion on entropy. So I hope that most of you have voted for this whole question. And unfortunately, majority. Okay, let me close this poll. So can you see the results on the screen? Property is not a path function. So those who have answered it as true, they are wrong. Property is independent of the path. Okay, so it is a state function and not the path function. So the correct answer is the answer should have been false. Okay, and 37% of the students have got this right. This is a very basic concept. You need to be very clear on this, because whatever we are going to discuss this, okay, that would all depend upon the discussion which we are having. Okay, so I'm sharing my whiteboard. Just tell me in the question column whether the whiteboard is seen. Just a minute. I'm having some problems with my am I audible, Pille ma'am? Pille ma'am, am I audible? Am I audible? वाइड स्क्रीन दिख रहा है आपको? नहीं दिख रहा? वही स्क्रीन दिख रहा है क्या? देखो. Okay, thank you. So what we are going to discuss today is what we had discussed earlier was the proof of Clausius theorem. Okay, let me write down this first. We had proved the Clausius theorem. Okay. And what is that theorem? This theorem is cyclic integral of del q by t. Cyclic integral of del q by t, provided the cycle is reversible cycle. Provided the cycle is reversible cycle is equal to 0. So this was proved. This was proved. Okay. Now what we want to prove is, we will be proving that there exists a property. We will be proving that there exists a property whose change is given by. We'll prove that there exists a property, okay, whose change is given by whose change we had proved the Clausius theorem, which says that cyclic integral of del q by t is equal to 0 for a reversible cycle. And what we'll be proving is there exists a property, and that property we would be naming as entropy. Okay, and that property would be naming as entropy, whose change suppose so there exists a property called as entropy, whose change, let us say, bias is given by this expression. Okay, it means that I want to prove that delta is to integral of del q by t for reversible. This is to be proved. Okay, to be proved. So this is a plan, and this is a very simple proof. Okay, and this is just based on our what is a property, and on the understanding of that, the first question was raised, that is, what do you understand by property, whether property is a path function or not. So if you had seen the videos carefully, let me rub this and let me go for proof. I'm rubbing this. Okay, so in the videos which were shown to you, there was a discussion on the properties called as pressure, which are the well-known properties. We talked about the properties called as volume, right? Pressure is a property you know. Volume is a property you know. These are the famous properties. Temperatures are the properties which you are encountering always. Okay, at least this you know. Okay, and now we are going to add in our bag, okay, our basket of properties, the property called as entropy. So we need to show that there exists something called as a property, which is a property called as entropy. So how do we prove this? How do we prove this? So for that, we need to understand that property means what? Property means it is independent of the path taken. Okay, so property is always independent of, is always independent of the path taken. Always independent of the path taken. It does not depend upon the path or the process. Okay, it is independent of the path taken during the change of state. Means, for example, if you consider the property of pressure or consider the property of volume. Okay, so let us say that we are talking about the property called as pressure. Okay, and let us say that there is an initial, I will be taking the same examples as were given in the video. Okay, so let us say that the initial pressure is 3 bar, 3 bar, and if you want to raise this pressure to 10 bar, 10 bar. Okay, and let us say that we are talking about lecture मध्ये. Okay. So let us say that the initial pressure is 3 bar and the final pressure is 10 bar. We want to compress, let us say, a fluid, it could be here for example, from 3 bar to 10 bar. Okay, so what we could do is that we could take a compressor. Okay, we can take a compressor, one compressor. I take one compressor of one company, and that compresses the given quantity of air from 3 bar, let us say state A to a final pressure, that is state B. So PA, pressure A is 3 bar and pressure B is 10 bar. Okay, so I am using one compressor. Okay, compressor of make, let us say, of some company, let us say Crompton Greaves compressor, right? One company. Okay, now somebody else also wants to compress this air from 3 bar to 10 bar, but instead of using this compressor, uh, uh, he or she is using some another compressor of some other company. Okay, so he would again get to this pressure, but by following some other curve. Okay, maybe the compressor is of different capacity. Okay, and he goes and he compresses by using a different compressor, and he goes back to the pressure P. Okay, so this fellow is using a compressor 2. Okay, compressor 2, and he is also compressing the given here from 3 bar to 10 bar. Third person would use a compressor 3, and he would take another path, obviously for compression, and that would again be from the initial pressure 3 bar to 10 bar. So what you say is that suppose I want to find the change in pressure. I want to find the change in pressure. Okay, so the change in pressure, how do you find? So you find the change in pressure by the final pressure, that is PB, minus the initial pressure, that is PA. And you are not worried about the path. Okay, so whether the path is the path A, path 1 followed by the compressor 1, or path 2 followed by the compressor 2, or the path 3 by the compressor 3. So you find that irrespective of the paths taken, this value PB minus PA would be the same. It means that, why is that so? That is because this PB as well as this PA, okay, they are the point functions. They are the point functions, or they are the state functions. They are not the path functions. They are not the path functions. It means that they are the properties. They are the properties of the system. They are the properties. So property, when you are saying that something is a property, when we are saying that something is a property, we are saying that pressure is a property, it follows that it does not depend upon the path taken. If you are saying temperature is a property, it follows that it will not depend upon the path taken. Okay, it is a function only of the initial state and the final state. Okay, so this has to be very clear that property is not dependent on the path taken. Okay, is this clear? Now we would be going to show that there exists something called as entropy, which is a property. Okay, so let me go to that proof now. I hope that this is clear. Kunal Gargi, Pranav, Mate, Ritesh Patil, whether this point is clear, what is a property and what is not a property? Okay, thank you, Ritesh Patil. Okay, so we'll go to this discussion on now. Uh, the proof, I mean, the proof that entropy is a property. Okay, so let me. So what we know from the Clausius theorem is that cyclic integral of this we are already proved del q by t for a reversible cycle is equal to 0. So please note that either I denote it by del q or I denote it like this dq and with the slash over here. Okay, so this means that it is an inexact differential. Okay, so both ways are correct. So in the videos you will find that uh, this sort of expression is used. Okay, so this is the same as this expression. Okay, so don't be confused about what are the notations which are being used. Okay, so this is a that the clause is then. Okay, so let us consider some reversible cycle. Okay, so let me consider one reversible cycle on a pressure volume diagram. I'm plotting it. Okay, and let us say that this reversible cycle we start from some state 1 or state A, let us say some state A, and via a reversible path R1 we reach a new state which is the state B. Okay, so this is one process. Okay, this is one process in the cycle. So I am assuming a cycle comprising of two processes. Okay, the cycle is comprising of two processes. One is a process A to B and other is a process B to A. Both these processes are reversible. Both these processes are reversible. Okay, now the second process, which is B to A, is also a reversible process. It takes you back to the state A, so that the cycle is completed, and that path is, let us say, R2. That path is, let us say, R2. Now let us apply the Clausius theorem to this cycle. Let us apply the Clausius theorem. Let me write down this. I am applying the Clausius theorem to the cycle, to the reversible cycle A R1 B R2 A. Okay, I am applying the Clausius theorem to this reversible cycle A R1 B. So what is that application? It means that what gives you is this cyclic integral of del q by t via the path R1 and R2 is equal to 0. Or let me rewrite it. It is the same as integral of del q by t, integral of del q by t via the path r1, via the path r1 from a to b, from a to b, plus integral of del q by t back to a, back to a via path r2, via path r2. Okay, so these two processes, because I have considered only 2 process cycle, it could be 3 process cycle, 4 process cycle, whatever. Okay, so this will be equal to 0. Why is this 0? Because this is what is the Clausius theorem, which we had already proved. Okay, so just now it's a rewriting thing. I'm just rewriting this using our elementary knowledge of mathematics. So let me write this like this, which can be rewritten as this: a to b, a to b via path r1, via path r1 is equal to minus integral of del q by t from b to a, b to a via path r2. And now what I'm going to do is that I'm going to get rid of this negative sign by changing this path. Okay, so getting rid of negative sign, what I will be getting is this, which is this would be now, because I'm removing the negative sign, so it would be from a to b via path r2 del q by t. Okay, so what you see is now that integral of del q by t, integral of del q by t from a to b, from a to b via path r1 is equal to integral of a to b via path r2 of del q by t. It means that this term, okay, let me choose some other color. It means that this term, okay, this term you see here, this term, this term, this term, okay, this term is independent of, this term is independent of the path taken. Okay, this term is independent of the path taken. Okay, so whether you are moving by reversible path r1 or r2 or whatever, okay, this as long as the initial and final state, as long as the initial and final state are the same, okay, this term is not going to change. Okay, this term would be the same. In other words, this is the point function, this is the point function, or this is the state function, this is the point function. This is going to represent the in other words, representing a change of some property. It is representing a change of some property. We don't know what property it is, but we know that for sure. We know for sure that this integral of del q by t along a reversible path, is showing a change of certain property. That property we don't know. That property we don't know. But let us call it as, we'll name it. Okay, so you can name it anything. Whatever is your favorite name, you can choose that name. But this fellow Clausius, he called that unknown property as entropy. Okay, and you can give it some other name, but he called it entropy and he denoted it by the capital S, capital S. Okay, so what we know now is there is some change in property delta S, okay, which is given by integral of del q by t, del q by t along a reversible path, okay. So this is the proof that there exists a property called as entropy, whose change is given by integral of del q by t along this integral. This integration has to be performed along a reversible path between the initial state and a final state, between the initial state and final state, for which we are interested in finding the property change. It means that in our case, for example, suppose this is A and B, and B, it means that SB, that is entropy at the state B, entropy at the state B minus entropy at the state A, entropy at the state A is equal to integral of del q by t from A to B via the path R. Okay, reversible equation. This has to be very clear. Okay, we are not yet talking about what is the absolute entropy. We are simply talking about what is entropy change, and we have not seen an expression for the entropy value. Okay, we are giving you an expression for the entropy change value. Okay, entropy change. The entropy change of del q by t, integral of del q by t, when integration is performed between the initial and final state via the reversible path. I hope it is clear to you. If it is clear to you, please say yes in the question column. If it is not clear, you can say no. Otherwise, saying yes. Okay. If your responses are not coming, maybe there are some net issues. I would be quickly revising this, and then I'll move to the next part of the proof. Okay. Okay. All of you are saying yes. Omkar is saying yes. Om Patel is saying yes. All right. See, I'll quickly revise this in case somebody has not followed this. This proof is very simple, and if you look at it from purely mathematical or logical perspective, then it is a two-step proof. Okay, it is a two-step proof. Now, what is to be proved is that there exists a property called as entropy, whose change is given by delta S is equal to integral of del q by t along a reversible path. Okay, we are not discussing what is entropy. We are not discussing the concept of entropy. We are simply arriving at the concept of entropy, or we are arriving at certain property from the second law concept, or more aptly from the Clausius theorem. Okay, so just as we had derived the expression of internal energy using the first law of thermodynamics, similarly by using the second law of thermodynamics, and more specifically the Clausius theorem, we are deriving the expression for a new property which is called as entropy. So we are introducing a property called as entropy because of the second law of thermodynamics. Okay, now what did we prove using the second law concept? We proved the Clausius theorem using the second law concept, second law of thermodynamics. And what is the Clausius theorem? The Clausius theorem is that if you take any reversible cycle, if you take a reversible cycle and do an integration for that cycle, the cyclic integral, then it has been seen that del q by t for a reversible cycle is equal to 0. That is what is the Clausius theorem. Now what we did is that we had chosen one cycle, a reversible cycle, and I represented that reversible cycle on a pressure volume diagram. Okay, and I have taken only two processes for simplicity. Okay, you can take any number of processes. I have taken only two processes for simplicity. Okay, and what is that cycle I had chosen? I had chosen a cycle A R1 B R2 A. Okay, this is the cycle, and I represented this cycle on a pressure volume diagram. Now, what is the next step in the proof? I have applied the Clausius theorem to the reversible cycle. This cycle A R1 B R2 A. So this is the reversible cycle. I am applying the Clausius theorem. Means what? It means that cyclic integral of del q by t for the cycle A R1 B R2 A is equal to 0. In other words, it is the summation of the process, that is A to B, integral of A to B del q by t via path R1 plus back to A del q by t via path R2, which is equal to 0. So now using our mathematics, we had taken this on the other side, it becomes negative. So what we get is A to B del q by t via path R1 is equal to minus integral of b to a del q by t via path r. Okay, removing this negative sign, what we see is that del q by t from a to b via path r1 is equal to del q by t from a to b again via r. It means that this expression integral of del q by t, integral of del q by t is independent of the path. It is independent of the path, or in other words, it is going to represent certain change in property. It is going to, because it is independent of the path, so it is a state function. It is going to represent certain property. Now, what is that property? So, you can call it anything, but this Clausius, he called that property here. We need to rename that. Okay, we need to give some name to that property. So he gave that name called as entropy. Okay, he called that property as entropy. So now we have the name for this expression. So integral of del q by t, integral of del q by t, we have the name which is entropy. Okay, so entropy change del s is equal to integral of del q by t. Okay, so sb minus sa is equal to integral of del q by t. Okay, so this is how we obtain the expression for entropy, and we showed that there exists a property called as entropy. Okay, this is a very mathematical approach of getting to this term, just as we have a very mathematical approach of going towards and discovering the property of entropy. Similarly, we have a very mathematical and logical approach of discovering what is called as a property called of entropy. Okay, now what is the significance of that? What it tries to tell us, that we'll be taking up later. Okay, now if it is an elemental process, okay, it means it's very small, this a and b, what we had done is that we had taken a finite kind of distance between difference between the state A and state B. If the state A and state B are too close, okay, too close, then we can write a generic expression, a small expression, which becomes like this, which is, this is the expression ds, okay, is equal to del q t, okay, for a reversible process, right? So this is a very important expression. This expression and this expressions, they are very important expressions of property change. What if the process is not reversible? And you know that in real life there is no process called as a reversible process. What if the process is irreversible? Can we still find the entropy change? Can we still find the entropy change? How to find the entropy change if the process is irreversible? Okay, so that, before discussing that, okay, I would like to test you, okay, for this whatever you have been asked. Let me put some poll questions to ensure that you are understanding the concepts. Okay, so I have launched the poll question before I take up the part 2 of the discussion. So pressure depends upon the path followed during a process. So as I had taken an example that pressure is a property and it is a point function, so it does not depend upon the path which is followed. Okay, and once you are specifying the initial state and final state, okay, initial and final state, then the pressure is going to be independent of the pressure change is going to be independent of the path taken. Okay, so let me close this. So the answer is false. The answer is false. Similarly, this this question about temperature. Similarly, this question about the temperature. Again, temperature, as I said, is a property, and it won't depend upon the path which is taken. It won't depend upon the path which is taken, or rather, if you want to achieve a temperature, if you want to achieve a certain temperature, let us say 50 degrees centigrade, you can attain it by different processes. Okay, so independent of the path taken, you can achieve a particular temperature. So again, temperature is also a point function. It is independent of the path function. So the correct answer is temperature is, being a property, is independent of the path which is taken. So let me close this and go to the next question. Now this is an interesting kind of a question. Net change in pressure during the Carnot cycle is zero. Now there are two options which are given. One option is that this is not possible, and the second option is that is so because the pressure is a property. So about 80% of the students have understood this, that the net change in process pressure during Carnot cycle, why it is zero. Okay. So let me share these results with you. I'll just wait for 2 minutes before I end the poll, and I will discuss this again because this is an important point we need to appreciate. Okay. Let me close this and let me share the answer is the net change in pressure during the Carnot cycle is zero because pressure is a property. Okay. So look at this white board. You see that I have drawn a Carnot cycle. Okay. And now what happens? This Carnot cycle means you know that Carnot cycle has 4 processes. Process A to B is reversible isotherm. Process B to C is reversible adiabatic. Process C to D is reversible isotherm, and process D to A is reversible adiabatic. A to B is reversible isotherm, it is expansion. You see that the volume is increasing from A to B. So during the process A to B, the pressure changes from, so initially the pressure was PA, it becomes PB. It becomes PB. So there is a lowering of the pressure. There is a lowering of the pressure. Then during process B to C, during process B to C, you see that again there is a lowering of the pressure. B to C, the pressure is lower. If you look at C to D, C to D, now what happens is that there is a pressure PC, you again get back to the pressure PD. So there is a pressure increase, and from D to A, what happens is it increases back to pressure PA. So if you look at this, the change in pressure, between any two points we take, this change in pressure is equal to 0 for a cycle. Okay, and this is because pressure is a property. So cyclic integral of dp is equal to 0. Cyclic integral of dp is equal to 0 because pressure is a property. Similarly, if you talk about volume, okay, look, if you talk about volume, what would happen to volume? Volume initially was VA, it would increase to VB, then from VB it would increase to VC, then again it will start decreasing, VC to VD, it is decreased, and again you come back to the initial volume. So delta V again is equal to, cyclic integral of dV is equal to 0. Cyclic integral of dV is equal to 0. It means why? Because volume is a property. Okay. So cyclic integral of dV is equal to 0 because volume is a property. Cyclic integral of dP is equal to 0 because pressure is a property. Similarly, when we are talking about the property of entropy, we would say that what we would say is this, that cyclic integral of del q by t is equal to 0. It means that this should be denoting certain property. And that property is nothing but entropy change. That property is entropy. Okay. I hope that this is clear. So this is how logically we arrive at the definition of entropy. So the answer is, if you take any cycle, if you take a thermodynamic cycle, you are getting back to the initial state, and then the changes in the properties, the total summation of changes in the properties will always be 0. Okay. Let me ask you this question. So del q by t is independent of path, true or false. Integral of del q by t is independent of path, whether it is true or false. So it appears that most of you understood this, that del q by t, integral of del q by t is a property, it represents the change in property, and hence it is independent of the path taken. And we had proved this, that integral of del q by t is independent of the path which is taken. Okay, so it is, the answer is true. Okay, the answer is true. Let me take the next question. Integral of del q by t is representing what? Integral of del q by t is representing what? Whether it is representing property or change in property. Whether it is representing property or change in property. Integral of del q by t is representing property or change in property. So you need to be quick in responding the questions, because your responses would be documented. Okay, and okay, let me share this result. Still some students are confused that they are saying it is a property. We are saying that it represents the change in property. Okay, it represents the change in property. We have not defined what is absolute entropy. We are just talking about change in the property called as entropy. This you need to be very clear on this. Okay, we have not defined what is property. We have defined what is change in property. What is change in property? Now let me go to the next part. Let me close this. So the answer is that integral of del q by t is going to represent a change in property. So again, this is a simple question, just to cross check that you are understanding it. I am very fast in closing the poll options because I have 3 more questions to finish up. Okay, so you need to be fast in answering. Okay, I am accounting for your net speeds while giving you the time span. Entropy change during reversible path, how to determine that? Those who are saying that it cannot be determined, they haven't listened to the lecture carefully. Okay, so the entropy change during the reversible path, this is what is also written on the board, that we can find the entropy change during a reversible path by taking an integration of del q by t along that reversible path. Okay, so the correct answer is it is the entropy change during the reversible path is given by integral of del q by t when the integration is performed for the reversible path. Okay, integration is performed on the reversible path. So that is how you get the entropy change. Okay, so the answer is entropy change during reversible path is integral of del q by t along the reversible path. Okay, let me close this and go to the next question. Now you have to think about the expression for entropy change, and then you need to talk about the units of that. You need to talk about its unit. Okay, the unit of entropy is what? That is the question. So most of you have followed this. Okay, most of you have followed this. What is the unit? But there are some still students who are struggling to understand the units. See, if you understood the expression for entropy, right, then, and entropy change rather, we had talked about the entropy change expression, but it is but a common sense that if you know the unit of entropy change, you can know the unit of entropy also. Okay, so the entropy change is given by entropy change ds is equal to dq by t, del q by t. ds is equal to del q by t, and the unit of q is joule. Unit of q is joule, and the unit of t is the temperature Kelvin, temperature in Kelvin. Okay, so obviously the unit of entropy is joules per Kelvin, joules per Kelvin. Okay, the unit of entropy is joules per Kelvin. If you are talking about specific entropy, that is entropy per unit mass, then in that case the unit would be joule per kg Kelvin. In that case the unit would be joule per kg Kelvin. But I had asked you the unit of entropy. So the unit of entropy is the unit of heat upon the unit of temperature. Unit of heat upon unit of temperature. Unit of heat transfer is joules, and unit of temperature is Kelvin. Okay, it would be joules per Kelvin, right? So please note that the unit of entropy is joules per Kelvin. Okay, so let me summarize what we had discussed so far. Okay, and then we will close the discussion. What we had discussed is, we had started with the Clausius theorem, and we said that the Clausius theorem is cyclic integral of del q by t for a reversible cycle is equal to 0. Then, making use of this theorem, we went on to prove that there exists a property whose change is given by integral of del q by t, and then we named that property as entropy, and we denoted it by the alphabet S. Okay, so it means that there exists a property whose change is given by ds is equal to del q by t, or if it is a if A and B are spaced apart, then SB minus SA or delta S is equal to integral of del Q by T from the initial state A to the final state B. Okay, so what we have seen today is how the property of entropy was discovered by using the Clausius theorem. Okay, how logically we arrived at the property of entropy using the second law of thermodynamics, using the Clausius theorem. We went on to prove that there exists certain property whose change is given by del q by t. Okay, so I hope that things are clear to you, and if they are not clear, I would recommend that you revisit the videos which are posted on your Google Classroom, okay, on your WhatsApp groups, and come back prepared. Okay, in the next class we'll do the next proof. Thank you very much. Have a nice day.